Hello everyone, my name is Aditya Nair. I'm an assistant professor in the Department of Mechanical Engineering at the University of Nevada, Reno. In this lecture, in this final lecture, I'm going to be presenting some turbulence modeling techniques. So a quick recap on conservation laws or governing equations for fluid dynamics. We have the conservation of mass, we have the conservation of momentum, and we have the conservation of energy. So these governing equations usually have to be solved in a coupled manner to perform computational fluid dynamics. So one method of performing computational dynamics or fluid dynamics is direct numerical simulations, or DNS. Now, direct numerical simulations resolves all the scales of the turbulent motion directly, right from the smallest dissipative scales up to the large energy containing scales. So it discretizes and solves the governing equations in the previous slide, or tries to do it exactly. Now, of course, there are accuracy issues and certain orders of accuracy that you can achieve with certain discretization schemes. But in general, direct numerical simulation requires very, very fine computational grids and small time steps, and therefore is computationally intensive. This simulation technique is currently not feasible for most practical engineering applications due to this high computational cost. Now, just to give you an idea of the cost, if you want to resolve a simulation in direct numerical simulation in 3D, the grid points scale as Reynolds number to the 9/4. So if your Reynolds number essentially increases, you can imagine how many grid points you would need to resolve the flow. So this becomes really computationally intensive. And also the overall cost scales as Reynolds number cubed. So if you had, for example, a Reynolds number of 20,000, Reynolds number cubed is a lot of time to accurately resolve all of the flow features for a problem. So, and I also show a graph of, essentially how many years it would take if you had a domain that was large enough where you had to resolve every scale. It would take years to compute. So DNS is generally not feasible for practical problems, but it usually gives, DNS gives us really good ground truth data that we can then use to develop turbulence models. So the large eddy simulation is a nice compromise between direct numerical simulation and what we'll discuss next, which is the RANS models. Now LES, which is large eddy simulation, it resolves the large energy containing scales of the flow directly, and it models the smaller dissipative scales. So the flow variables in LES are decomposed into a resolved part and what is called as a subgrid scale part. Okay, so you can see that this is unlike doing any kind of modal decompositions that we discussed before. Here you have u, which is a function of space and time, the u bar, which is this filtered field, is also a function of space and time, and then you have essentially these fluctuations, which is u prime, again a function of space and time. Now, when we substitute this into the Navier-Stokes equation or the momentum equation, we get the filtered momentum equation in terms of just the resolved part. You'll see that there is almost a correspondence, exact correspondence between the terms in this filtered momentum equation and the original equation, except for this last term, which is called as the subgrid scale tensor tau. Okay, so this is the closure problem for LES, is how do we determine tau from the resolved scales of my data or of my flow. So this subgrid scale tau has a form in terms of this. So usually, these subgrid scales need to be modeled using, say, data-driven techniques. The third way to do this, to do CFD, is the Reynolds averaged Navier-Stokes equation. Now, Reynolds averaged Navier-Stokes models all the scales of turbulent flows. It models it and solves, and usually what you get at the end is an equation for the time averaged or mean flow. So the flow variables in this case are decomposed into a time averaged part, which is only dependent, the only spatially dependent part, which is time average, and a fluctuating part U prime. And when we substitute this into the Navier-Stokes equation, you get again an additional term. This term is called as a Reynolds stress tensor, which again needs to be modeled. Now, the Reynolds stress tensor represents the effect of the turbulent fluctuations on the mean flow. It is used to account for additional momentum transfers due to turbulence. Now, RANS models in general are pretty fast to solve. And they describe the time averaged flow behavior well, but they are less representative of details of the flow physics, right? But still, if we can get, if we can model this Reynolds stress term correctly, we can get kind of an overall idea of how the flow evolves. So this leads us to a closure problem. So how do we get the subgrid scale tensor as well as the Reynolds stress tensor in these LES and RANS models? So we're not lost. We have a starting point. So the starting point is there are some available common closure models that people have thought about before in terms of describing the subgrid scale tensor. So for example, this is an LES closure model called as the dynamic Smagorinsky model, where the stress tensor is described in terms of the resolved strain tensor, which is this S bar variable, and a filter width. So there is a constant term here, which is CS, which is either imposed empirically or can be determined using data-driven techniques. So there's a lot of scope for using data-driven techniques to refine this subgrid scale tensor, right? So this model can also be simplified in terms of its representation. All the terms in the subgrid scale model before the S bar term is also called as eddy viscosity. So you can model the eddy viscosity term, and by modeling the eddy viscosity term, you get directly the subgrid scale tensor, which will close the LES model. A common model for Reynolds averaged or the Reynolds stress tensor in RANS models is the Boussinesq hypothesis, which states that the Reynolds stress tensor is related to the mean strain rate of the flow. So if you have a time averaged mean, you get the mean strain rate. So there is a relationship between this Reynolds stress and the mean strain rate through this again, this mu t, which is the eddy viscosity term. So again, in both of these LES closures and the RANS closures, usually you'll see a lot of concepts centered around modeling eddy viscosity, additional eddy viscosity. And this makes sense because we are trying to model the small scales. So we are trying to model these extremely small dissipative scales of the flow, and we need to model their dissipation rates accurately. So if we can model them, which is the eddy viscosity, essentially this additional viscosity that needs to be modeled, then we can get our turbulence working correctly, and we can perform either large eddy simulations and RAN simulations, but we don't need to perform full DNS. So our goal is to kind of achieve the performance of DNS without the computational expense or cost. So both of these stress and tensors, like I said, arise due to averaging or filtering operation in RANS and LES respectively, and both need to be modeled to close the system of equations. Now, the choice of the model can significantly affect the accuracy of the simulation. So there is a great scope to do really precise, accurate, data-driven turbulence models. So just reiterating, this mu t is the turbulence eddy viscosity term, and K here is the turbulent kinetic energy. So I want to end this kind of lectures with some examples and successful examples in terms of building data-driven turbulence closure models. So the first example is for a 2D isotropic turbulence problem. Now in this case, the authors used a stencil of vorticity and stream function along with information of two eddy viscosity kernels as inputs to neural networks. So they used a neural network architecture essentially to close the turbulence models. They predicted the subgrade vorticity forcing dynamically both in time and space. And what we see is the neural network effectively mapped the grid resolved information to the turbulence source term. So it really accurately kind of modeled the eddy viscosity term that in a data-driven way, we're comparing it to DNS results. Now, by statistically analyzing these, the average kinetic energy spectra, the neural network showed really promising results. So usually when we look at these problems, we look at a kinetic energy scaling of, negative thirds for 2D flows and negative 5/3 for 3D flows. And you can see that the neural network essentially retains most of, it models a fair amount of information of what the true spectra should look like. In this paper also, an optimal neural network architecture was determined by sweeping over, or alternatively sweeping over the number of neurons and the number of layers. So I would say this paper or this work has been successful in some sense to model the eddy viscosity terms using neural networks. Now, this is this closure idea with neural networks or machine learning tools was also explored in a more recent work on 3D isotropic turbulence. So in 3D isotropic turbulence, they used a formulation called as the multi-agent reinforcement learning formulation, or MARL, as an automated tool for discovering the turbulence models. What they did is they implemented, this multi-agent reinforcement learning on LES simulations for 3D turbulence. They used the statistical properties of the direct numerical simulations as a reward. So if you can reproduce those statistical properties, your model's getting better. So this is a classic reinforcement learning strategy where you have some reward function that essentially gets maximized by subsequently performing multiple iterations, and ultimately you get a model that performs really well with the highest reward. And this highest reward in this case is again to recover the statistical properties. Now you can almost make out a common theme here. When I talk about turbulence modeling, we don't talk about the exactness of the dynamics because we're talking about turbulence, right? Turbulence is a state of disorder of the system. So there's always when we discuss turbulence, we think of disorder. So you can't have exact representations of the dynamics, but what you can have is an exactness in terms of the statistical representation of the system dynamics, and that is what most of these models are striving for, even in the last 2D turbulence work as well as in this 3D turbulence. So in this work, like I said, it's a reinforcement learning strategy. The closure problem is enacted as a control policy, essentially, by incorporating agents that identify critical spatiotemporal scales. And the learned turbulence models, not only work for certain cases, they exhibit some generalizability because this is a reinforcement learning problem. By maximizing this reward, they have demonstrated that you can increase generalizability across both grid sizes and flow conditions. Now, we talked about neural networks and reinforcement learning as to do this closure problem or solve this closure problems. But there are other ways also to solve all this problem. I also highlight this other work where which uses this data-driven covariance completion problem for a turbulent channel flow. So what the authors do is they construct stochastic dynamical models in a data-driven manner to essentially replicate the second order statistics of the turbulent flows. So what the authors do is they develop a framework to complete unavailable second order statistics consistent with linearization around the turbulent mean velocity in channel flows. So I want to reiterate, unpack that. You have channel flows, we linearize the governing equations around the turbulent mean velocity. And then we try to, model the second order statistics using this stochastic dynamical model framework. So what they do is they incorporate colored in time excitation of the Navier-Stokes equation, and this is viewed as a low rank modification to the generator of the linearized dynamics. So usually in this community of input-output modeling or resolvent analysis in fluid dynamics, usually you think about the nonlinear term as being some kind of external forcing. So the nonlinear term, I mean this convective term in the Navier-Stokes equation as some feedback external forcing to the linearized dynamics. And that is the same viewpoint that is enforced in this work. So what this work is able to do is it's able to give us a data-driven refinement of first principle models, and it's able to replicate essentially the normal stress profiles in these channel flows. All right, so a quick recap of what we covered in this chapter. I know that this was a fairly smaller lecture, but there are plenty of other techniques and other papers that talk about data-driven turbulence modeling. I just gave you some ideas about different eddy viscosity models, other data-driven matrix completion methods that have been used for turbulence modeling, but there are many others by groups by Karthik Doraisamy in University of Michigan and others who've done a lot of great work in data-driven turbulence modeling that I have not talked about. So I would recommend you to check out all of these papers and develop your own innovative techniques to do turbulence modeling. And it's an excellent test bed. And machine learning and AI in general and data-driven techniques are a great test bed or a great tool for this turbulence modeling closure problem. So quick recap is we covered the closure problem, we covered the role of data-driven techniques in this. So hopefully in this lecture series, I have motivated you that there are a lot of different types of models for modeling different aspects, both high dimensional and low dimensional aspects of fluid flows. And hopefully, you follow the pipeline of data generation systematically, dimensionality reduction, reduced order modeling, turbulence modeling, in a systematic manner, you follow this pipeline. Of course, I haven't covered a lot of different tools, which is, processing not noisy data preparation in terms of removing outliers, processing experimental data assimilation techniques. So there is a lot of topics that, I have essentially swept under the rug, but are of equal importance in this data-driven modeling community for fluid flows. So I encourage you to join that. Fluid dynamics is an excellent test bed for applying data-driven modeling. And just as future thought is these models essentially give us tremendous scope for data-driven flow control, which we can incorporate control theoretic aspects into these data science, network science based reduced order models that we obtain and combine them to develop optimizations of system designs. All right. Hope you enjoyed the lecture, and I will meet you at the next lecture series.